apropos to Harvard and quantum thermodynamics, and Dudley Hirschbach, who was sitting right there. Charming story. One of the great atomic physicists of my time was a man named Pipkin. He was over here at Harvard and did beautiful atomic physics experiments. One day he's looking at the numbers and he realizes that the binding energy of sodium to make diatoms is about 2 electron volts. And his gas is about a 40th of an electron volt kinetic energy. So he figures, well, it must be everything is molecules. So he calls Dudley. He says, Dudley, is it true that most of my stuff is molecular? And Dudley says, Pipkin, you haven't learned about free energy. That's why we teach free energy instead of energy. You've got to put the entropy into the game. So you see, the whole business of quantum thermodynamics is more important than you might otherwise realize. And now we're going to get another beautiful example at that kind of interface, this time with...
There's going to be a lot of free energy there.
Yes.
Okay, thank you very much. First, I would like to thank the organizers, of course. This is really a fresh talk. So it's a bit special in the sense that I'm trying to give, it's a kind of a unified framework approach. So I will try to give a kind of broad perspective on the field of quantum thermodynamics from this framework of repeated interaction. So I will also make contact with different experiments that have been, or setups that have been considered by other people, and try to somehow look at them into a as general way as possible. And this work is a common work with Strasberg, who's now postdoc in my group, Schaller, Brandes, who unfortunately passed away, and myself. Okay, here we go. So I don't need to go through the introduction. I guess you all know why thermodynamics is important. The only point I want to mention is that people like me are not only interested in quantum thermodynamics, but more generally on thermodynamics of small systems, even if there's no quantumness in these small systems. And typically, this is very important in biophysics, where fluctuation play a very important role, and to understand how this molecular machinery works, tools and concepts which are very similar to what we encounter in quantum thermodynamics can be also used to understand these biosystems. And there are quantum effects also there, but mostly at the internal level of the molecule. So the outline is the following. I will start by a kind of small summary of the standard setup system with reservoir, and show how to go from exact identities to quantum master equations, and trying to convince you that it's important to have an effective theory in terms of the system degrees of freedom only, of quantum thermodynamics, not only these abstract exact identities, but that nevertheless they are needed to get the right thermodynamics attached to the quantum master equation. And then I will move to this repeated interaction framework, where I basically split the system, or X, my previous system, in two pieces, one which is what I rename now the new system, and these units that come, interact with the system, and then move away. And they can be prepared in any state, and so it's interesting to see from a thermodynamic point of view how they're going to influence the thermodynamic description of the system. In other words, here you expect to have things like work and heat, but here you will have more general things, and we want to characterize these more general effects on the thermodynamics of S. And same thing, exact identities, and then move to quantum master equation. And then I will show you how, using this framework, I can make contact with different setups that have been studied in the literature, information machine, maser, and electronic Maxwell-Demon. Okay, so first, the traditional setup system reservoir. So exact identities, we take an Hamiltonian, that we split in three terms: the system, the reservoir, and a coupling term. I allow time dependence in both the system and the reservoir Hamiltonian. And very important, that's actually the assumption. I assume that my initial condition of the entire setup is factorized. Can be anything for the system, but product with an equilibrium state for the reservoir. And if I define my energy of the system like this, it's a priori not obvious because I decide to put the interaction energy in the system. Might be questionable, and one can discuss it for a long time why to do that. But one of the reasons is that one gets a consistent second law, because with this energy, one can split the evolution of this energy in terms of work, where the work is really the total energy change in the system. So that's really the energy that is put by this time dependence in the system. So it's a kind of meaningful notion of work. It really comes from this time-dependent driving, semi-classical if you want. And heat, which is the amount of energy that goes into the reservoir. So this is really the derivative of the energy going into the reservoir. So it also seems meaningful. And using these definitions, you can actually prove that this quantity, the entropy production, sometimes the dissipation, or sometimes the entropy of change in the universe, can be written as the entropy change in the system minus the heat divided by the temperature, which you can interpret as what goes into the entropy change in the reservoir if you apply equilibrium thermodynamics for the reservoir. That's how it's justified in traditional thermodynamics. But you have this quantity, so that makes sense. That's what I would call a second law for non-equilibrium transformation, and you can prove that this is always greater or equal than 0, because it's a relative entropy, and it's a relative entropy which is appealing for the following reason. You see that it's a kind of measure of the information that you lose by having an exact description of your system, but assuming that your bath is at equilibrium. So if you compare the exact state of your full system to the exact state of your system, but saying the bath I don't care, I put it at equilibrium, this is kind of the measure of how different these two things are. And it's precisely the notion of entropy production that characterizes this. So I think from a conceptual point of view, it's also quite interesting. You can further split this in the relative entropy between the real state of the bath and its equilibrium state, and the mutual information between the system and the reservoir. Now, this is a little trick which is useful to send one important message, which is a non-equilibrium state is a resource. You can introduce the free energy as energy minus T. Beta is inverse temperature, so this is temperature times entropy. It's non-equilibrium because E and S a priori can be for any state of the system. And you can, with this definition, it's trivial to rewrite the second law as work minus this change in free energy, in non-equilibrium free energy. And then you notice that if you compare the state of the non-equilibrium free energy to the state of the equilibrium free energy, where the equilibrium free energy now is the exponential of beta of the system Hamiltonian. This is why I put this additional condition, assumption 2. Now I assume that my interaction was turned on and turned off at the end of the transformation, precisely to make contact with this Gibbs state, which is the free Gibbs state without interaction. Then you can rewrite this dissipative work, it's sometimes called. This is the one that you encounter typically in equilibrium thermodynamics, because it tells you that you start and you end at equilibrium. And so the work that you perform during such a transformation will always be positive. This is the standard result. But now, by simply rearranging this expression in this way, you see that you have this relative entropy of the final state, which is always positive. This one is also always positive. We just showed it. But you have this term here that is negative. So this means that this term, in principle, can allow you to make this contribution negative. So in other words, if your initial state is out of equilibrium, it means that during a certain transformation, you may actually extract more work than if you have to go from an equilibrium state to another equilibrium state. The ideal work extraction would be if you make sure that you end in a new equilibrium state and that everything is reversible, so this term is also 0. If not, you have this additional thing. But the message is, if you can really think of a non-equilibrium state as a potential resource to extract work more work than anything you could do during a reversible transformation, or a transformation going from an equilibrium state to another equilibrium
So
state.
we have a plethora of time because one talk is canceled.
Okay.
So I'd like to set an example. I don't understand this first equation. Can you go back a view graph?
Sure. Yeah.
So where does that come from?
So it comes from substituting heat by using the first law. You see, if I take
Right, but
heat,
the next view graph,
yes,
you have F instead of S
and you
and
see
Q.
F I define as E minus TS. So it's only substituting. I don't have a
That's fine, but then how does that get to go with work?
because the work comes from the first law here. Oh, work is here. So if I substitute heat here by the first law, I get that heat minus heat is work minus energy. Then I combine energy with entropy to create my free energy, and I get the next relation here, which is work minus free energy. Okay? So it's interesting, this fact, to think of the non-equilibrium state as a resource, and it's also useful to think of these feedback processes of Maxwell-Demon. Why do they allow you to extract things? Because basically by measuring you create non-equilibrium states, and so you can extract from these non-equilibrium states that you observe by measuring. That's one way to think about it. But let's continue. Now, these identities here, they are exact given these assumptions, but they, an object like this, I need to know the dynamics. To calculate an object like this, I need to know my full system reservoir dynamics, which I typically don't know in practice. So it's quite important to try to get equations only for X alone. And this is really the canonical thing. I will not go into the details because I'm sure 99% of you know exactly this by heart. But the point is, if you have a system Hamiltonian where the time dependence is slow, have a weak interaction, you can go through the standard weak coupling master equation theory, sometimes von Markov secular it's called, and you can get a closed equation for the system density matrix with this super operator that can be written this way, the Bath correlation function. You have the property of local detail balance for the Bath correlation function because your Bath is at equilibrium, and you can show that the Gibbs state is the invariant state of your dynamics if you don't have driving, and there are certain validities for that, and this goes back a long time. It also goes back a long time. The fact that you can build a consistent thermodynamics attached to these kind of master equations. You define, now it's like the special case of what I said before, but where you neglect the coupling strengths because the coupling strength is weak. So the system energy is only the expectation value of the system Hamiltonian, the entropy is still the Shannon entropy. You can write a second law where now the work is this the time dependence of the system Hamiltonian only, and the heat, you don't have access to the bath anymore, so it's not anymore the change in the heat, in the energy of the bath, but you express it in terms of the energy change in the system, so the fraction of the change of energy that goes to the bath is what you define as heat. And you can also write the second law. Now it's a stronger second law because you can not only prove that the integrated entropy production is positive, but also the rate of entropy production is always positive. And you get this known form for the entropy production that people like Spohn, Lebowitz, and Anitsky here obtained a long time ago. Also Lindblad had such a relation in his papers. If you want a review of this, because I went fast, you can look at quantum thermodynamics using these quantum master equations. You can look at these very nice review papers. And you can also, in this paper, find the study of fluctuation theorems for this kind of master equations.
So are you applying that this last equation here is equilibrium? This is an equilibrium.
Yeah, this is the Gibbs state of the system. It's the same invariant state of my master equation.
But in Robert's talk, he was making the point that it's much stronger. How do you deal with that?
Because, and we will get to that in the repeated interaction, the bath is not an equilibrium bath in what we were discussing. And I will also look at that, but this here is really equilibrium bath weak coupling, there we expect a Gibbs state. Okay, so master equation. Now I move to the repeated interaction framework. So as I said before, let's split my X into two parts, and I assume that I will write everything for the one interaction, and then we can simply iterate. So we imagine that we have this unit coming, interacting with S, then moving away. So it's simply a matter of renaming X by S and U, and it's obvious that you can introduce the mutual information here, since initially you assume that the unit and the system were uncorrelated. In this change of X, entropy of X, you have the change in the entropy of S, the change in the entropy of U, and the change in the mutual information, but since the initial mutual information was 0, you only get the mutual information after the interaction between S and the U that goes out. And the second law is like that. And for the first law, you make sure that you count energy change just before the unit starts interacting and just before the new one arrives, so that you basically eliminate the problem of the strong coupling, because you switch on and you switch off. And in that case, you can really split the energy of the system X as system U of the change in the unit plus the change in the system, which you can decompose as work and heat. And here the important thing is that in the work expression, you have two contributions. You have the one that comes from time dependence, if you have one, during the time where the system and the units are in contact. Very often this is actually not in the models that we will consider, so you can even put this to 0. But there's this switching, I call it switching contribution. So this is only, these integrals are only there to say that it's everything except the boundary effects. The boundary effects are taken care of by this switching work, which is really the work that you need in order to switch on and then switch off the interaction. Okay? So because before we saw that work, the general definition of work was really the change in the entire energy, but we have time dependence here and here. So since the units come, interact, and then leave, it's like switching on and switching off, and this guy is precisely counting for this work contribution of switching on and switching off. And the heat is the change in the energy that goes into the reservoir, so that one doesn't have boundary effects. Now, a simple reordering of what we just had here. This was for the full X thing. Now I reorder. My change in the energy of the system is work plus heat plus what changed into the unit. So we see that this is the new term arising from this interaction. If you look from the perspective of system S, it's like we have a new source of energy coming from the unit. And if you now define entropy production for S, you can basically only take the previous one and move this term is always positive. And because in repeated interaction, once the correlation, so the mutual information is established, you never use it because you don't manipulate the units after they went away. It's like lost contributions. You cannot use this as a resource. You can basically put this on the other side, and you have that the notion of entropy production for your system is the change in the system entropy, the change in the unit, that's the new contribution, and the heat. So but what these units do here is create this new term and this new term, and we still have that this must be always greater than 0. And this can be viewed as the effective thermodynamic description of this system interacting not only with a heat bath, not only with the time which is heat, not only with the time-dependent force which is work, but also getting energy and entropy from these units. And now, okay, at steady state you can further simplify this because if you can actually show that under reasonable condition this system will reach a steady state. And at steady state the system quantities stop changing after at every periodic, let's say every time after the interaction, the system is again in its previous state before the interaction. So these contributions are 0, so this actually can be rewritten in the following way. So SS is for steady state. This positive quantity is the work minus now this free energy change in the unit. So this means that now we have a resource, this free energy here, that really comes from the fact that you can prepare this unit in an arbitrary state. And you have different limiting cases for this resource. The one where the free energy is completely energy dominated. This is what we will call a work reservoir. As Avitsky was saying this morning, this is what you would call the reasonable definition of work, an object that gives energy without corresponding entropic contribution. The other extreme is the information reservoir, which is an object which only gives an entropic contribution without energetic contributions. And then you have a continuum in between, and there's also another class of interesting units, is the thermal ones. You prepare your units in thermal state. You can prepare them in a temperature that is different from the temperature of the reservoir with which your system is in contact. And in that case, you can actually prove that the maximum efficiency of the machine, defined in the Carnot sense as the work you can extract from the energy coming from this state, is going to be always lower than the Carnot efficiency. So you recover also from this identity the standard constraints. And you can prove that if the temperature is the same, you cannot extract work. So basically, if these units are thermal and at the same temperature of the bath, there's no way in which you will extract work because the free energy change will always be positive. You know, so it's a classification scheme. It is a little bit in the spirit of what you did with Defner, this classification of the different resources. But I think it's a nice way to think, to see the different limiting case of this resource that is stored in the units. Now, let's start looking at different special cases. The first one, the Landauer principle, that's a trivial one, because that's the case where you assume that there is no energy change in your unit. One trivial way to do it is to make these levels degenerate, so that when they come, there can not be any energy stored in them. So in that case, you can immediately see that the work is going to be always greater or equal than the change in the entropy of the unit. And if you want to erase, this is the problem of Landau, he wants to erase information, so he wants to decrease the information in the tape, you need to put positive work, always greater or equal than the entropy change. And if it's 2 level, you get the famous log 2. And the heat also expelled in order to erase is bounded by this change in the entropy of the units. So that's a very simple application. A more involved one is the scheme of feedback control, where you separate the interaction into 2 phases, one which you call the measurement, and another one the feedback. So this means that during the first measurement, it's very generic, because measurement is any interaction will do the job. Basically what this interaction does is create a mutual information between the system and the unit. But then the feedback can be implemented in the following way. That's the way in which people implement coherent feedback control. This is a specially tuned Hamiltonian, such that depending on the state of the unit, it implements a certain operation on the system. So it's conditional. So the first thing correlates the system with the unit. I forgot to say the crucial thing, that I again assume that these units have no energy in them. The measurement correlates the two. The feedback, depending on how the correlation was established, implements an operation which depends on the state of the unit. And then you can write this second laws that I obtained for the measurement operation, quite generic, for the feedback one. And you can actually show that you can, at steady state, you can show that the work that you can extract during the feedback period here is bounded by these three terms. One is this one, which is well known, but you also have these two contributions here, the change in free energy during this phase and the change in entropy in the unit during this phase. You recover the result by Sagawa and Ueda, who showed that the work that you can extract during a feedback process is bounded by the mutual information. If you assume that your measurement is not disturbing, this is precisely setting this delta F there to 0, because the measurement should not disturb the system, then this is 0. And if your memory is classical, this means that the projection is not going to affect anything. And so the change in the unit entropy during the feedback process is 0, then you recover the Ueda-Sagawa. So it's a way to think of their result as a special case of these more general second laws, where we basically split the interaction into two phases, measurement and feedback, and as often there is this central role of the mutual information coming in. If you look at the entire process, you sum the measurement and the feedback, you realize that you're dealing only with an information machine, because the work is bounded by the change in the entropy of the unit. Okay, so this was, in a sense, still identities. Let's now, as I was saying, in practice, it's very important to show that we can get effective description in terms of the system, closed dynamical description for the system, in order to make contact with other experiments where we don't have information about the entire universe. And one interesting limit is the limit where these units are sent with Poissonian distributed times. And when they interact, we assume that the interaction is very strong, it's a delta kick. So using this assumption, you can actually derive a master equation for the system. So you can show that the density matrix of this system satisfies a closed equation, where this is the standard generator caused by the heat bath, but this generator is now caused by the interaction with these units. Very fine, so we have a closed dynamics. The point is we can also get a closed thermodynamic description, and I will not go into the details because, to understand really what is going on, one has to really analyze what this means. But the main point is we can again write the second law, which has the same shape as what I was describing before at the level of identity. The work from the time dependence during the interaction, the switching work, the heat, and this entropy change from the unit. Same thing for the second law, the change in the system entropy, the change in the entropy of the units, and the heat. And here is the first important message. I didn't go into the detail, but if you would try, if I would give you this master equation here as a mathematical object, like a Lindblad quantum master equation, the natural entropy production that you would come forward with, most likely, would be something like that. You remember this is the shape of this entropy production that come from Lindblad or Leibovitz, Salitsky, traditional formulation when you interact with the heat bath. This is not this entropy production here. So the message is that it is important to know the original definition of heat, work, entropy in order to take the right limit in which you can derive the master equation and do the same operation on all of these quantities to get the right thermodynamics. It's very hard from the dynamics to infer the thermodynamics. That's my message. It's important to know the thermodynamic identities and take the right limit on them to get the right thermodynamics corresponding to the dynamics. Okay, another interesting thing, this is, actually I have to say, Juan Paondo came to Luxembourg and we had very interesting discussion, so I owe part of this thing to him. We realized something that is, I think, interesting. You can calculate the entropy change in the unit by really saying, okay, I'm interested in the entropy change in the unit that passed, and that's it. And that's what you would get if you take this quantity. So this is after the interaction, the state of the unit, and you take the difference between after and before, and that's your entropy change. But there's another approach which is a bit more global, and it's like, okay, let's call NT the number of units which interacted with my system. And this is, I know the rate with which my unit comes, so I know how many of these units interact after time t. And this is basically the fraction of my units that interacted. This is the fraction of the units that did not interact. And I ask, what is the entropy change in this population of units with this fraction of units that interacted and the fraction that did not interact? And then you get something that is slightly different, because here the entropy is given by this. So you see it's different from here, because here we have this term here. Here we don't have this term here. It's like taking, again, rho u here. And if you compare the two definitions, you get this relative entropy, which you can interpret as a kind of mixing entropy, because you can imagine that if your unit interacts, you put it back into the soup, and this entropy here, this entropy change here, or this one, is like the collective entropy change of the soup. So they are not the same, and this one, this difference is always positive. And if you now look at thermal units, you get that only if you use this soup approach, the mixed population of units, you can then recover the standard connection between the entropy change and the energy change that corresponds to the notion of an ideal bath. So in other words, this is telling you that if you really want to treat these thermal units as an ideal bath, you also have to keep in mind that in the way in which you calculate your entropy change, you have to not only look at the entropy change of the unit that interacted, but of this soup of units. It's a subtle difference, but this term appears in various places, and it's kind of interesting to have a clear idea of its meaning. So that's why I wanted to make this comment. Another limit is we can do it two ways. One, from what I showed you before, is take the limit of very frequent interaction. It was Poissonian, now you send them more and more frequently. And that's one way to take the limit, so from our previous formalism to this one. But actually you can show there are certain assumptions, because else you get divergences when you take the limit. So I need these assumptions, and in particular notice I remove the reservoir, because it also creates problems. So here I remove the reservoir, it's only units interacting with the system. So I get these kinds of scaling for my unitary evolution, system interacting with the units. But this is also equivalent, this limit, to regular interactions, simply interactions where you switch on, as soon as a unit passes, you send the next unit, and you switch on and switch off, and you scale the interaction in this way. So this is like a step function of with delta t, and you divide by square root of delta t. So it's a different scaling, but in this scaling you can also derive a closed master equation, which is different, but still, not only you get a closed dynamics, you can also get a closed thermodynamics. So you can apply this operation to all the thermodynamic quantities, and you get different expression for all the different works. And again, you have this switching word appearing. And also, since there is no bath here, you see that the entropy production here is a direct measure of the mutual information. So the entropy production of this master equation is the rate with which the mutual information is lost. Okay, so this was the formalism. Now, let's move to applications or illustrations. The first one is the Mandel-Jarzynski. So it was interesting for us, Chris and Dibiendu, when they did this model, they used stochastic thermodynamics. They used rates with the idea, when they write the property of the rates, that whenever this system does a clockwise rotation, it's basically lifting a weight. So it's the notion of work comes via these rates. Here we can actually design a certain system, a certain tape of two-level system, degenerate, and a certain interaction in such a way that the master equation that I derived before reduces exactly to your master equation there. And since Chris solved it analytically for us, you only have to, to go and check his paper, you can actually prove that if there is an entropy increase in the tape, you can actually lift a weight, except that I don't lift a weight in this formulation. The work here is really this switching work for turning on and off the interaction. So we have an Hamiltonian formulation of what Chris was looking at, and for us the work is really this work spent by switching on and off the interaction. Okay. Next. The maser, this is actually thanks to you. You showed us that one could extract work from coherences. I can basically use the same kind of system. I prepare this three-level system units with a coherence between B and C, and I use this as my initial state of the unit, which I send. Of course, in practice, what it means is that this is not thermal, because I have this coherence here, but I prepare coherent atoms that come and interact with the cavity. And my cavity is my system, and one can use the master equation I was using before for this system, calculate the master equation, and calculate the occupation of the cavity given these units that come and interact with the atom. And one actually recovers exactly the result that was in Scully's paper, that if there is a coherence between B and B, one gets a non-thermal population in the cavity, but in presence of the coherence, one gets a non-thermal population. And the argument is that out of this non-thermal distribution in the cavity, one can always do an expansion, for instance, of the cavity and extract work out of it. That part is not modeled here, but the point is to show that with these coherent units, one can actually pump. It's a non-equilibrium state because of the coherence. One can actually create a non-equilibrium population in the cavity that can be used to extract work. And now the third application, this is a model that I've studied a lot and that Jukka Pekkola discussed this morning. It's this, Jukka did a very similar model experimentally, and recently there's another experimental group who did also a very similar model. So the idea is that we have this is what we call our system, and we have electrons that, if this guy was not here, would go from higher to lower chemical potential. But because the electrons are capacitively coupled with another dot in contact with another reservoir at a colder temperature, this interaction is such that we can pump electron against the bias. And it has to do with tuning these barriers, because what the demon does, the interaction is tuned in such a way that it's essentially equivalent to lifting and closing the barrier. But we can describe the full thermodynamic of the process. If you describe the full thermodynamic of this process, it's actually a thermoelectric device, because you have a thermal gradient and you have a bias, chemical bias. So you're using a thermal gradient to pump electrons across a bias, and you can study this as a machine. But the interesting thing is that there is a regime where you can tune the interaction such that there's essentially no energy exchange between these two systems. And so if you only look at this system, something weird is going on. The energy balance is okay, but you see your electron going against the bias, and you can show that this is a purely entropic effect. And you can study the performance with which this hidden degree of freedom pumps things across against the bias. Already here you have these two notions, the effective entropy production of this system, where you imagine that somebody is tuning the barriers, but you can also access the full entropy production of the entire device, because you have the mechanism of the demon. You don't need to do anything. There's no external driving. The mechanism is there, but there is a cost for it. So this relates to the discussion that was going on this morning. The entropy production of the full device tells you that there's a cost for it. And you can actually compare. This is the line for certain parameters. This is the voltage. This is the region where the work is negative, so you are pumping electrons against the bias. This is the entropy production, the effective one, that you would guess if you only watch this guy, and you see that something weird is going on because somebody is tuning your barriers, you would get this line. But if you now, which one is it? Capacitive. So it's this, I think it's green, I'm colorblind, so I don't know. This line is the one for this model, where you really look at the dissipation of the entire device. And you see that there is a cost because the hidden mechanism is dissipating, and the difference between these two lines is precisely the cost for the mechanism for running the daemon. But this was the traditional experiment setup, and here what we did is we basically engineered a tape, so a repeated interaction scenario, where our units are degenerate, and in such a way that the interaction will give a master equation which is essentially the same as this one. But it's a different mechanism. Now we are implementing the same Maxwell-Demon effect, so the effective dynamics is the same, but the mechanism for the demon is different. And we can compare the cost for implementing the two mechanisms, and the cost for the repeated interaction one is this blue line. We were actually quite surprised that they are not so far off. We thought that the mechanism could be very different, but nevertheless, even if we change parameters, the two costs are comparable. Okay, so this is the end of the example, and now of course, to trigger a good discussion at the end, let's make a slightly provocative claim, although I think it's very well proved in this framework, but there are of course many things to say about it. Let's consider the following question: classical versus quantum resource. So we want to extract work, and we saw that the work extraction is related to the free energy of the units. So if we want to have the most powerful resource in a system, in a unit made of n levels with a certain n ranked energies, what we want is basically maximize this difference. So we want to maximize the initial free energy and minimize the final one. So the maximum free energy will be reached for the uniform distribution, and that's a simple case. It's a classical state. The minimum of the final one, it's an argument by contradiction. Let's assume that I have a minimum that is a quantum state. So I say, okay, I have a quantum state that minimizes the free energy. Well, now I build the corresponding classical state, which is simply the same state but without the coherence. And this state has the same energy because of this, but we know that the entropy of a quantum state versus the classical one is always lower. So we basically show that there is then that the classical state that we've built is actually lower than the quantum state, which basically means that the lowest state has to be a classical state. And so in that perspective, the classical resource is actually better than the quantum one, because you get the most out of the free energy for a classical resource. Yes?
You know, of course, terminology, but I think quantum and classical should be used in sort of proper way. Because if you take a pendulum, like as classical it can be, which oscillates back and forth according to the definition, it's quantum. Because of course it has all diagonal.
It's true. Here the definition is removing the coherences, and it might not be always the most relevant way to define classical. But that's a generic problem that we have when we want to define what we mean by comparing classical with quantum. But you know, that's a clear statement for n levels that with coherences you will always get a smaller.
But this is in the end state, no? I mean, when you talk about the resource, you talk about the initial state. Whether you coherence in the initial state that you will consume will help you, yes or no. And of course, it's better to go to a diagonal state where you consume your coherence.
Yes, but also initially, the thing that maximizes your initial state, your initial free energy in the unit, is also a classical state.
It can be, but if it's not, I can use it. I can use it and bring it into a classical state and gain some work out of it. For example, there's the Janet protocol, right? That allows you to go to the same diagonal elements while getting work out of the coherence using a thermal bath, of course.
Okay, using a thermal bath, this is why you have to define a setting.
Yes.
And the setting here is you have these end states, and you basically want to know, okay, what is the maximum free energy I can put in? What is the minimum free energy that I can get out? And you end up with classical and classical. That's the way to get the biggest difference. That's the statement. And of course there are zillions, and of course there are many other ways in which quantum effect can do things that classical things cannot do, but at least within this framework, I think it's a very well-defined question with a very well-defined answer. For power and things like that, you can also get differences. But in this way, you get this result. So let me conclude. I knew this would trigger some discussion. Okay, so that's the summary, right? We started system reservoir, and we had standard heat and work. I showed you that with these units, we get new sources of energy and new sources of entropy, which can allow us to look at different limiting cases. The Landauer principle and the feedback control thermodynamics can be viewed as special cases of this formulation. Then I showed you that we had different limits where we could get a master equation, a closed description for the system, and a closed description for the thermodynamics. This I skipped, but I nevertheless say, we also showed that you can engineer the tape in such a way that it creates the same effect as a time-dependent Hamiltonian. So you can set your tapes, prepare your units in such a way that when they come and interact with your system, the effect for the system is like having a time-dependent Hamiltonian with a certain function that depends on time, which is set by how the units are prepared. Because you can really show that there is no entropic contribution, only energetic contribution. So you can build, it's a bit artificial, it's a bit of a mathematical trick, but you can build the same effect of a time-dependent Hamiltonian using preparing accurately your units.
By preparing, you mean putting in a particular sequence,
yes, exactly.
encodes a particular time-dependent.
Yeah. And then I showed you various applications, and the take-home message is, I think the nice thing about this repeated interaction scenario is that it allows you to have a kind of overview of the different things. And again, I emphasize that these exact identities, they are important. First, from a conceptual point of view, they reveal the connection with information in thermodynamics. And second, they are needed to obtain the right thermodynamics starting from a given kinetic description. If you only have the quantum master equation, it would be very hard to recover the right thermodynamics if you didn't know where you come from. And I also think that it's important for quantum thermodynamics to have effective description for the system, because typically these identities in the full state, for practical purpose, they are not very useful. So it's important to make contact with these effective theories. I think for quantum master equation, things are well understood. Non-equilibrium Green's functions are tough. We have some work on that, but there is still work to be done at that level. And I think that's it. Thank you very much for your attention.
I'd like to go back to Robert's paper, which I happen to have here, the 79 paper. There, he defines the energy as the trace of the density matrix H0 plus little h of t. It's important that he has a part of a Hamiltonian member which involves time.
Yeah.
And then he says, work, what's that? Good work, that involves little h dot, the time derivative of the Hamiltonian integrated over time. And the entropy comes from the Liouville operator operating on the density matrix. Now, where do we see that? I see pieces of it, but where do you most naturally see that in your work?
Here. Here. Right, so this formula, where you trace the change of the system Hamiltonian over the system density matrix. So
Right.
that's the same definition.
Good. So
this is all. This is basically this.
So the heat piece
Yeah.
is here,
Yeah.
and now I would have thought that this is going to operate on H.
No, you see, this is the change in the density matrix So it's, if you want, you can do it this way. The energy is the trace of the product of the energy with the density. The work is the part of the change that is due to the time dependence in the Hamiltonian.
Yeah.
The heat is the part that is due to the time dependence in the density matrix of the system. And actually, classically, we do it similarly in stochastic thermodynamics.
And now you're explicitly taking d by dt to be a little operator.
dVdt, you mean the interaction?
Yeah,
To be small, yes.
Okay.
This is master equation, so it's small interaction. Yeah.
good. Now, you said that you were going to discuss why and when this is beta and when
Yes.
it's more general.
So in this repeated interaction scenario here, voilà. Let me use this one for instance. So when I have these units that come interact with my system, I still get a master equation with a Lindblad generator here and here. But in this case, these units, I can prepare them as I want. They are not thermal states. And so the steady state of this master equation is not a Gibbs state. So the invariant state of d rho dt of rho equals 0 is not the Gibbs state. So these are non-thermal dynamics. And this is the reason why the entropy production curves of these dynamics is not of the form that I described before, like this, with a steady state distribution, the difference between the log of the rho and the log of the steady state. It's of a different kind.
About the implementation of time-dependent Hamiltonian with repeated interaction, does this transformation, well, the initial state depends only on the unitary that you want to implement, or also on the initial state of the system, and you have to kind of specially tailor it?
No, the
depending on
system not. It's really the units that are specially tailored.
Yes, but the state of the units depends on the initial state of the system?
No, not
Or
on
just
the
on the
state of
unitary
the
that
system.
you want to implement?
So it goes like this. Let's say the system Hamiltonian is HS, and I want to put plus A times F, where F, A is an operator, F is an arbitrary protocol. There is a procedure to prepare the unit state in such a way that after a certain time they implement the F.
Yes, but
So
this will work for any
independently
initial
of
state
the-
of the system?
Yes, it doesn't not depend on the initial state of the system. Yeah, I see. Yeah.
So let's thank our speaker again.